Hello everyone, welcome back to Chem Story. Today, we're diving into a really important concept in organic chemistry, resonance structures. Sometimes, one Lewis structure just isn't enough to show how electrons are actually spread out in a molecule. When that happens, we use resonance structures to show the different possible ways electrons can be arranged. Understanding resonance is key when it comes to predicting how stable a molecule is, how it might react, and how electrons move around in organic compounds. Alright, let's get started. A resonance structure is one of several valid Lewis structures that represent the same molecule. Some molecules can't be accurately described with just one arrangement of electrons, so we draw multiple resonance forms to show the different ways electrons can be arranged. These forms are connected with double-headed arrows to show they're not separate molecules, but just different ways of representing the same one. And sometimes, we use square brackets to group them together, to make it clear that they all contribute to one overall structure, the resonance hybrid. For example, in the acetate ion, the negative charge isn't stuck on just one of the oxygens. Instead, it's shared or delocalized between the two oxygen atoms. Same idea with the nitrate ion. The negative charge isn't sitting on just one oxygen. It's spread out evenly across all three. That kind of delocalization gives us a much better representation of the actual molecule than any single Lewis structure would. While resonance structures help us picture how electrons can move around in a molecule, the real molecule doesn't actually flip back and forth between them. What really exists is a resonance hybrid, a kind of blended version that takes all the possible resonance forms into account. It's like a weighted average of those structures, which means the electrons aren't stuck in one spot, they're delocalized across the molecule. So instead of having separate structures, the resonance hybrid shows one unified electron cloud, where the electrons are spread out over several atoms, not locked into a single bond or location. For example, in the acetate ion, the negative charge isn't just sitting on one oxygen, it's delocalized between the two. In the resonance hybrid, we show this delocalization by drawing dashed lines between the carbon and both oxygen atoms to represent partial double bond character. We also place a partial negative charge, delta minus, on each oxygen to indicate that the extra electron density is shared equally between them. This gives a more accurate picture of the real electron distribution in the molecule. Similarly, in the nitrate ion, the three oxygen atoms share the negative charge equally. In the resonance hybrid, we show this by using dashed lines between the nitrogen and each oxygen to indicate that all three NO bonds have partial double bond character. Now if we take a closer look at the formal charges, in each resonance structure, nitrogen consistently carries a +1 charge. So in the hybrid, nitrogen also carries a +1 overall. As for the oxygens, in each resonance form, 2 of the 3 oxygen atoms have a -1 charge. So if we average that out, each oxygen ends up carrying a partial charge of about -2/3. That's why, in the resonance hybrid, we place a -2/3 charge on each oxygen to reflect the equal sharing of the total negative charge across all 3 atoms. This gives us a much more accurate picture of how the electrons are really spread out in the molecule. When we draw resonance structures, there are some rules we need to follow to make sure everything's accurate. First off, every resonance structure has to be a valid Lewis structure. That means it still needs to follow the usual rules, like the octet rule, especially for second-period elements. Of course, there are a few exceptions. For example, boron often ends up with fewer than 8 electrons, and elements like phosphorus or sulfur can have expanded octets, since they're in the 3rd period or beyond. So as long as each resonance form respects those basic guidelines, it can be considered a valid structure. Another important rule is that in resonance structures, only the electrons move. The atoms themselves stay in the same place. So pi electrons and lone pairs can shift around, but the positions of the atoms don't change, and we never break or form sigma bonds. Also, the total charge of the molecule has to stay the same. Even though formal charges on individual atoms might change from one structure to another, the overall charge of the molecule doesn't go anywhere. Take the nitrate ion, for example. No matter which resonance structure we draw, the total charge always stays at -1. What really defines resonance structures is how the pi bonds and lone pairs are arranged. Double bonds, lone pairs, or even unpaired electrons can shift from one position to another. but the actual connectivity between atoms always stays the same. We're not breaking or forming new sigma bonds. We're simply showing different ways the electrons can be rearranged within the same bonding framework. One key rule to remember is that electrons move from areas of higher electron density to areas of lower density. So negative charges tend to shift toward atoms that are either positively charged or neutral, often to form new pi bonds. Keep that in mind, and your electron flow will make sense, which means your resonance structures will be both accurate and chemically reasonable. Now let's talk about how to actually draw resonance structures, starting with how electrons move, and the key rules for shifting them the right way. The most common patterns usually involve electron movement between 2, 3, or 5 atoms, depending on the molecular setup. So let's start by looking at a 3-atom system, one of the simplest setups for resonance. A classic example is a carbanion intermediate. Here, the negative charge on a carbon can be delocalized through the movement of pi bonds. The lone pair on the negatively charged carbon moves in to form a new pi bond with the carbon next to it, and to maintain proper valency, the existing pi bond shifts over to the next carbon, pushing the negative charge there. So structurally, what we see is that the negative charge, originally on carbon 1, has effectively moved to carbon 3. This movement spreads out the electron density and helps stabilize the molecule. You'll often see this in conjugated carbanions and enolate structures, where that kind of charge delocalization plays a big role in reactivity and stability. In the case of a carbocation intermediate, the positive charge can also be delocalized through resonance. Here's how it works. The adjacent pi bond donates its electron density by shifting toward the positively charged carbon. That forms a new pi bond, and the carbon that originally had the double bond now ends up with only 3 bonds, which creates a new carbocation center. So structurally, you can think of it like this. The positive charge that started on carbon 1 has now shifted over to carbon 3. This type of resonance is super common in allylic and benzylic carbocation, where the ability to spread out the positive charge makes a big difference in both reactivity and stability. Now let's take a look at how to draw resonance structures that involve radicals. In this case, it's the unpaired electron that sets things in motion. It triggers the nearby pi bond to shift, and that movement leads to a new pi bond forming between adjacent carbons. At the same time, one of the electrons from the original pi bond, the one that didn't get used in making the new bond, moves over to the next carbon atom. So what we end up with is the radical effectively shifting from carbon 1 to carbon 3. This kind of delocalization helps spread out the unpaired electron, which gives the molecule extra stability, just like how charge delocalization works in other resonance systems. The idea of electron movement in these resonance structures can go even further, especially when you're dealing with a conjugated system that includes an extra double bond. In those cases, the delocalization isn't just happening over 3 atoms. It can stretch across 5 atoms or even more. This extended delocalization helps spread out the electron density even better, which makes the entire system more stable. Now let's move on to resonance structures where electron delocalization happens between just 2 atoms. A classic example of this is seen in protonated carbonyl compounds. In this case, the pi electrons from the carbon-oxygen double bond shift over to the oxygen atom. That makes the oxygen, which was originally protonated and positively charged, neutral again. The carbon, now lacking that shared electron density, appears to be more electron deficient. Now keep in mind, this doesn't mean the carbon has completely lost its electron density. It's just one way of representing the molecule using resonance. In reality, the true structure is a hybrid, where the electrons are still partially shared between the carbon and oxygen. But still, this resonance form helps us understand why the carbon becomes more electrophilic, and that's why it's more reactive toward nucleophiles. This kind of resonance plays a key role in acid-catalyzed reactions, because it shows how the carbonyl group's reactivity can change through charge redistribution. Another good example is the phosphine ylide. In this case, the electron density in the carbon-phosphorus bond shifts toward the carbon atom. As a result, the carbon ends up carrying a negative charge, while the phosphorus takes on a positive charge. This kind of electron movement is what gives the ylide its unique stability, and it plays a key role in the Wittig reaction, where phosphorus ylides react with carbonyl compounds to form alkenes. Now, let's take a look at benzene's resonance. This is a classic example of aromatic stability. In benzene, the pi electrons aren't just stuck between individual pairs of carbon atoms. They're fully delocalized across all 6 carbon atoms, forming a highly stable conjugated system. So instead of having alternating single and double bonds, the resonance hybrid spreads out the electron density evenly. That's why all the carbon bonds in benzene end up being the same length. This delocalization gives benzene extra stability and makes it way less reactive than a typical alkene. Now let's talk about how to compare the stability of different resonance structures by focusing on a few key factors that affect resonance stability. Not all resonance structures are equal. Each one can have a different energy level, and the more stable a structure is, the more it contributes to the overall resonance hybrid. In general, the more valid resonance structures you can draw, the more stable the molecule tends to be. That's because delocalizing the electrons helps spread out any charges and lowers the overall energy of the system. So when you're evaluating resonance, keep in mind that stability plays a big role in how much each structure matters. The most stable resonance structure is the one that contributes the most to the resonance hybrid, and there are a few key features that help us figure out which one that is. First, a complete octet makes a structure more stable. So we prefer resonance forms where all atoms, especially second period elements, satisfy the octet rule. Second, fewer formal charges mean greater stability. If we can avoid unnecessary charges, that structure is going to be more important in the overall hybrid. Third, a negative charge should sit on the most electronegative atom, like oxygen, not carbon, to make sure the electrons are distributed in the most favorable way. And finally, the closer opposite charges are to each other, the better. Shorter distances between them help stabilize the structure through stronger electrostatic interactions. Understanding these principles of resonance will really help you as you dive deeper into organic chemistry. And with a bit of practice, predicting stability and reactivity is going to start feeling a lot more intuitive. Great job today. Keep practicing, and I'll see you next time.